This tutorial is going to demonstrate how to do a two-way repeated measures ANOVA in R. The repeated measures ANOVA is used for analysing data where the same subjects are measured more than once. For example, you might have measured individual self-esteem scores, which would be the outcome or dependent variable, on 3 time points during either dieting or not dieting to determine whether their self-esteem improved. A two-way repeated measures ANOVA is used to evaluate simultaneously the effect of 2 within subject factors on a continuous outcome variable. So in the example above, our 2 within subjects factors would be time and either dieting or not. The assumptions of a within subjects ANOVA are that there are no significant outliers, that the outcome or dependent variable is normally distributed, and that the variance of differences between groups should be equal. So the first thing that we need to do is install and load the packages we need for this tutorial. We will be using the Datareum, RStatics and ggpub-r packages. To install them, you simply type install.packages and in brackets and quotation marks the package name. And then to load them, you can type library and then in brackets the package name. Remember that if you've already installed a package, you do not need to reinstall it, as the R environment will remember it. But each time you want to use it, so for example when you're starting a new script, you do need to load it in using the library function. For this tutorial, we are going to use the Self-Esteem 2 dataset, which can be found in the Datareum package. This dataset measures self-esteem scores over 3 time points in both control and diet trials. We can use a two-way repeated measures ANOVA to determine whether there is a significant interaction between diet and time on the self-esteem scores. But first, we need to convert the data to a data frame and then we can view it. To do this, you can use the piece of code below. And remember that view has a capital V. So this is what our data looks like. Here you can see participant ID numbers, which are repeated because this is within subject's design. Next is the treatment condition, which is either control or diet. This is which time point the score was taken at. And finally, score is our self-esteem scores. Before we run our ANOVA, we first need to check the assumptions. So firstly, let's check that there are no outliers. You can do this by using the identify outliers function, as you can see here. And here are our results. As you can see, there are no extreme outliers, and we know this because 0 rows have been returned. The next assumption we need to check is that our outcome or dependent variable is normally distributed. And we can do this by using the Shapiro-Wilk test, like this. And here are our results. As you can see, self-esteem scores were normally distributed at each time point except for time 1, as this p-value is less than 0.05. But please do remember to check whether your supervisors have different cut-off points. We can also check normality by creating QQ plots. Sometimes this is a better method than using Shapiro-Wilk, especially for larger samples. And this is because the Shapiro-Wilk test can become very sensitive to even a minor deviation from normality. QQ plots draw the correlation between the data and normal distribution. And you can tell R you want to do a QQ plot by using the ggqqplot function, like so. And here are our QQ plots. As you can see, all of the points fall approximately along the reference line, so we can assume normality. The final assumption we need to check is that the variance between groups is equal, and this can be done using OUTLIERS test. However, we do not need to do anything prior to running the ANOVA, as it will be automatically computed during this process. And by using the get ANOVA table function to get your results will mean that the greenhouse geyser correction will be automatically applied to all factors violating this assumption. So now we are ready to run the ANOVA, and we can do this by using the ANOVA test function like this. And here are our results. As you can see, there was a statistically significant two-way interaction between treatment and time, which is shown on the final line of the output. And because of our significant finding, we can run some post-hoc tests to see where the significant difference lies. So a significant two-way interaction indicates that the impact of one factor, for example, treatment, has on the outcome variable, so in our case self-esteem scores, depends on the level of the other factor, so for example time, and this would be vice versa. So you can split a significant two-way interaction into a simple main effect, where you run a one-way model of the first variable at each level of the second variable, and then if the simple main effect is significant, you can run multiple pairwise comparisons to determine which groups are different. So here's the post-hoc test for treatment. First, we are running a simple main effect where the results look like this. And as you can see, there is a simple main effect of treatment was not significant at time 1, but it was significant at time 2 and 3, which can be seen from the p-values here. Then we are running pairwise comparisons. And this is the results. As you can see, mean self-esteem was significant between control and diet at times 2 and 3, which you can see from the p-values here. Remember that when running multiple comparisons, you should use the p-adjustment method Bonferroni, and this will correct your p-value to allow for these multiple comparisons. You can also repeat the same process for time. And here are the results. As you can see, the effect of time is only significant for the control trials, but in the control trials, all pairwise comparisons were significant. So here is the full code used in this tutorial that you can use and copy to have a go yourself.